If you are currently learning dynamic programming, aka DP, I want to share with you something I think you may want to pay attention to. But before we start, notice that this video is not an introduction to dynamic programming. When some people first learn DP, in order to make sense of the algorithm, they tend to draw out the DP array and trace the iterations. This method can be beneficial for beginners, that's why many instructors do it, but if you find yourself always drawing out DP arrays on your scratch paper when solving DP problems, you might not be doing the optimal thing. Because DP is such a fundamental idea, DP problems can be extremely easy or extremely hard. Just visualizing the arrays instead of understanding the abstract nature behind the algorithm can make it hard for you to improve. When you later get to more complicated DP problems, for example, bitmask DP, you would find it almost impossible to understand. So, how to avoid this pitfall? If we can't draw out the arrays, how do we think about DP problems? Well, the short answer is, you have to get used to thinking abstractly about subproblems. Here's a trick. Think about DP arrays as black box functions with parameters rather than actual arrays. Again, think about DP arrays as black box functions with parameters rather than actual arrays. Let me explain it through a classic DP problem. If you feel like you have already understood what I mean, then you can treat the following problem as an exercise. So the problem goes like this. You have a bunch of marble piles arranged in a straight line. Each pile has a weight, represented by an integer. In each step, you can choose two adjacent piles of marbles and merge them. The cost of this operation is the sum of the weights of the two piles. You want to eventually merge all the piles into a single pile that contains all the marbles. For example, for the first step, you can choose to merge these two piles, and the cost of this operation is 9 plus 11, which is 20. And of course, after you merge these two piles, they become a single pile with the weight equals to the sum of the two original piles. Next, you can merge these two piles. This step costs 20 plus 7, which is 27. Then you can merge these two piles. It costs 46. Then maybe these two piles, which cost 58. Finally, merge the last two piles with a cost of 63. Sum up the cost of every single step, we get a total cost of 214. However, if we choose a different sequence of operations to merge the piles, we might get a different total cost. For example, like this. And we get 173, which is less than before. The problem is asking you, what's the minimum total cost to merge all the piles? You can pause the video and think about it for a while. Okay, at first glance, the problem might give you an illusion that it's solvable using some greedy criteria. For example, what about we always merge the smallest piles, so that we don't have to carry around that big weight in the following steps? Unfortunately, since the permutation of piles can be arbitrary, smaller piles can be in between large piles. One or two large piles might precede small piles. There's no simple greedy criteria to solve this. So, we should somehow consider all the possible operations. Apparently, if we just simulate all possible operation sequences, the algorithm is not going to be polynomial. But that's exactly what dynamic programming is for. It allows us to try all the possibilities without expanding all the operations. So here, we use a two-dimensional interval dynamic programming, where dpij means the minimum cost to merge all the piles from index I to index j to a single pile. For example, dp24 stores the minimum cost to merge these three piles. dp15 stores the minimum cost to merge the last 5 piles. Obviously, our base cases should be the intervals of lengths 1. because it doesn't cost anything to merge a single pile to a single pile because it's already a single pile. Now, if I just give you this completed DP algorithm, how would you proceed to understand it? If you start drawing the 2D array on your scratch paper to trace the code, you're actually making this way too complicated than it should be. So let's throw that away. First, let's look at the loops. We can see that the outer loop is looping through the possible lengths of intervals starting from 2 to n. And the inner loop is looping through the starting point for a fixed interval length. So together, they iterate all possible intervals in this order. First, all intervals of length 2, then 3, then 4, then 5, and finally 6. This line of code is just calculating the weight sum of the piles in this interval. In actual implementation, we can calculate this in O of 1 with a pre-calculated prefix sum. But here, in order to focus on the DP, just think of it as a O of 1 function that returns the weight sum of the piles in this interval. For example, get stone weight sum 1, 2 would give you 33 plus 1, which is 34. We calculate this value for future use because no matter what your sequence of operation is, the last step to merge the last two piles into a single pile is always the total weight of all the piles in this interval. You can play with a few examples if you don't find that immediately obvious. And for a fixed interval, we loop through the possible midpoints to split this interval into the left half and the right half. Then, we have the most important line of code in our algorithm, the DP transition. Instead of drawing out the DP array and the tiny arrows, recall that I said at the beginning of the video that you should think of accessing DP arrays as making function calls. So, instead of accessing some 2D array with row index left, column index right, we can think of it as calling a function with two parameters left and right. We can assume that after some magical operation, this black box function returns the correct result, which is, as we specified earlier, the minimum cost to merge all the piles from pile left to pile right into one single pile. So let's look at this step of DP transition with the help of that mental trick. Now, we can think of DP left, mid as calling the function and passing in left as left and mid as right. So the function returns to us the minimum cost to merge from pointer left to pointer mid. And similarly, DP mid plus 1 right calls the magic function and gets a result which is the minimum cost to merge from pile mid plus 1 to right. So overall, we are adding the minimum cost to merge the left half to a single pile and the right half to a single pile, plus the cost to merge the left half and the right half to a single pile. We traverse all the possible splitting points mid to find the minimum cost. This trick helps you with the design of DP algorithms too. All you have to do to make a correct DP algorithm is to make sure two things. First, with multiple correct values from the magic function, you can create a new correct value, very similar to mathematical induction. Second, you can get your final answer to the problem with one or multiple magic function calls. Particularly in this problem, we get the correct value of dpij by looping through all possible split points and calling the magic function on the left half and the right half. And we get our final answer with one magical function call, dp0 and -1. In summary, if you want to improve in solving DP problems, you have to get very comfortable thinking abstractly about subproblems. And drawing out the DP array is not helping you with that. This method of thinking about DP arrays as functions is, of course, just a mental tool to help you get there. If you're comfortable thinking subproblems, then all it takes to design a DP algorithm is figuring out what dimensions define a subproblem and then connect the subproblems together properly. Harder DP problems are nothing more than stacking a bunch of additional key observations on top of that basic procedure. Okay, if you enjoyed this, remember to click subscribe. See you soon.